The topic for today is fixed effect model. Remember, we are looking at the factors that are used to control the unobserved factors, the models for that. Fixed effect controls for all variables that are fixed over time. It controls for them. Variables that vary across individuals but are not varying across time. So variables that are fixed over time, they are controlled for. What are variables that are fixed over time? Culture. Okay, sometimes you want to incorporate the cultural element into the data. Religion is fixed over time. And usually when we speak of over time, we are talking about over a 1 year period. Geography, climate, gender, race, quality, ability, skills, behavior. These variables are usually fixed over a time period of 1 year. Now, if the unobserved heterogeneity, which is these factors, if these factors are correlated with one of the independent variables, the XIT, OLS will be inconsistent. The OLS will be unbiased and inconsistent. And so what we do is that we use something known as a fixed effect model. The fixed effect model is also called the within estimator model. So you model the fixed effect, and then you can add the time dummies to control for time. You can add binary independent variables inside, just as you would have done with any other thing. The most important thing is that the variables that are fixed over time are controlled for. So, although the time constant variables cannot be included in a fixed effect, so you can't include religion, you cannot include race or ethnicity, okay? You cannot include gender. These variables are perceived to be constant over time, okay? Even though you can't include those factors over time, you can interact those variables that change over time with other variables, like say with dummy variables, like year dummies. So let's say the year dummy, the year is 2005, and this variable is religion. And you have a dummy for religion. You can interact religion with time so that you check how religion, when it is happening, when it is changing, okay, it's not changing. Religion is not changing, but you check whether religion changes over time. You check whether religion changes over time and how that will affect the potential dependent. So let's remember ourselves with a general panel model. Okay, this is the general panel model. That's a general panel model. We know that this first XIT, the dependent variable is Y, the regressors are XI, there are many of them. The unobserved heterogeneity is the UI. The time dummy, the symmetric time dummy is lambda T, and the idiosyncratic noise is X. If somebody is talking about panel data and they don't mention these three items, the compose error term, punish them, critique the work. So how do we formulate the fixed effect model using the general approach? Well, first thing you want to do is to find the average of the variables across time. Remember, you want to remove the time, the variables that don't change across time. So you're going to find the average. And when you find the average, you represent the average with a bar, which means that the variable is changing with time. So this is it. So if we have Y, we'll find the average of the Y. And when the Y is actually YIT. So when we take the average of YIT, we call it YI bar, where the bar is indicating the time, the T. The same thing with the XIT. The XIT, when we sum them, and find the average, we now get XIT, XI bar, where the bar is a T. Now the lambda is with T, and the epsilon is with T, okay? And so when we sum them equally, we get the same thing like the rest. And when you do that, you are now going to get this YI bar equals XI bar with a beta. The mu I is not having a bar because the mu I does not change across time. This is the individual error component. And And then, of course, the time dummy and the idiosyncratic variable. So have we put it there? The UI doesn't change with time. So its average over time is the same UI. Now, when you look at this equation 1, just a second. Maxwell, you have a question. So you have your equation 1 here. I'm going to take each of one of these values minus the bar, the yi bar. Then I'll take this xit minus the xit bar. Okay. So that's what I'm going to do here. So that's what I've done there. Yit minus the yi bar. Then the beta multiplying xit minus the xi bar. The u minus the ui. The u minus the ui is going to cancel. And then the lambda minus the lambda bar, and then all of that. So I take this equation 1 minus the equation 2 here. And when you do that, you're going to get something like this, okay, with some tilde sign, okay, with some tilde sign on top of the yit. So all of this, all of the yit minus yi bar, you make it yit with a tilde sign. This equation 3 is the fixed effect model. This equation 3, that is a fixed effect model. Now, if you are writing some of these models into a journal article, then it will be nice to have the first equation, then you take the average, and then you can now have the second equation, can deal with the transformation, okay, the within transformation, and then you can now have the fixed effect model. This is the fixed effect model. And you can now estimate this fixed effect model using the pooled OLS. Okay, using a pool, because you've transformed the data. Okay. And this is becoming something. So the beta parameter you will get from this becomes the beta cap W, where the W is the within estimator. It's not like the usual OLS beta that you have. Okay. Now, please note that this lambda T with a tilde sign, okay, this lambda T with that tilde sign, the lambda is made up of several time dummies. Okay, so the lambda is made up of, each of the time dummies, and of course their respective coefficients. We know this from previous modeling. Okay, we know this from previous modeling. Okay, but the most important fixed effect model is what I've just shown you in equation 3 here. Remember, under the fixed effect model, the general one becomes this. The general equation, which you see at the top here, becomes, this should be epsilon, by the way. It becomes this, where you can now see that the UI has been pulled out of the composed. Okay. The UI has been pulled out. So if I were to write my entire model for the wage pan equation, you can see that in this modeling, I have removed all the fixed factors. Okay. Previously, there was education, but I've removed education because last time we gave a reason why education is not considered as a continuous variable. Also, we don't have experience, even though we have experience square. We explained this the last time. But then we have union because a student can change. So union is a changing variable, a varying regressor. And the married is also a varying regressor because these are children who marry over the period. The fixed effect estimator eliminates any fixed invariant or time fixed invariant, time fixed variables from the model. So the time fixed variables, experience, education, a lot of them have all been wiped out. But like we said, we allow time varying variables into the model. Also think about why experience is dropped, although experience square is not dropped. We made that point clear the last time. The other thing is you notice this. Oh, why experience dropped? Is here. It is assumed that when we include a full set of year dummies of all years by the first, and you guys will note that even though we had 1980, we included the year dummies for all of them in the model. And you can see this here. Let me just show you. You can see the year dummies of all the model here. However, we did not include the 1980 year, which is the first year. Now we started from 1981. Okay. And the point of that is that if that is the case, we can't estimate the effect of the independent variable that is changing across time. We expect that that is, even though it's supposed to be, changing across time, the changes are constant. The changes are constant. And so when it comes to the experience, every worker, every year, okay, every worker every year is increasing his experience by 1 year deterministically. Everybody. And so that makes experience constant over time. And like I said before, even for first difference, because first difference takes its inspiration for fixed effect. When you run the model and you add experience, it's not going to work because it is assumed by the software package to be perfectly correlated with experience work. Okay, so fixed effect can really be an interesting thing. Okay, of course, how that affects the results is up to you and the results. If the assumption is made clear, it's made clear. You can use pooled OLS estimator to solve for this. So, ladies and gentlemen, I'm going to give you different formulae for working with a fixed effect model in R. The first one is everything. The only thing is that you don't have the experience, the education, you don't have that. Okay, you don't have any of those. The experience, the union, and the education, the experience and ethnicity, those are all fixed. So we didn't include them. All right. So we're going to run this model. This model assumes that the effects of the heterogeneity effect is individual. So there is individual heterogeneity. That's what the first one is. The within shows that we are dealing with a fixed effect. The time, which is another one for the effect, is showing that we are focusing on time's specific factor, the unobserved heterogeneity related to time. And then the two ways is the one that will deal with both of them, both the time and the individual. Okay. And I brought the last one here. The last one here, I don't indicate whether it's time or individual, but it will still be dealing with the individual. So this is the command. Now let's go to our R to run the results and interpret these results. So this is the first one, only time. This is only time effect. R square has reduced, you can see that. R square has reduced there. You can see clearly that all the coefficients are significant. However, there's no time dummy. You can see the time dummy have been removed. This was a deliberate act to remove that. Because, and why is that so? Let me just tell you here. Because we incorporated the fact that we are dealing with a time, okay? And so if we are dealing with a time, there's no need to incorporate that element as well. Let me take you to the next command. The next command was the individual specific factor. So that one, we want him to check for the, remember, these models are stronger than the usual OLS. They are stronger, they are robust than the usual OLS. So let's go and look for the individual specific effects there. This is it. And this one, it includes the time and all that. This again is fixed effect, but you include the time because your focus is on the individual factors. The focus is, and this time when you look at the R square is bigger than the one we just did some few minutes ago. The R square is 18%, but I just said R square is smaller. But the good thing about this is I look at the values, look at the significance. Everything is significant. Everything is significant in this behavior. The next thing is to do the two-way effect, and the results will be the same as the one that you had not even done. The one you did not specify whether it's two-way. So let's do the two-way effect, and this is a result. It's not that fine and friendly, but you can see that it's omitted all of the time variables. Okay. And then the last one. Now, somebody might be wondering why all of this? Well, the reason is that you want to be able to have flexibility in the model. All right. Now, there's something you want to know, that even though you have done all the fixed effect, and the fixed effect is to capture unobserved heterogeneity. However, the model might not be robust. Guys, when I say that any model might not be robust, what it simply means is that the model might have issues related to heteroscedasticity and autocorrelation, which gives us the opportunity now to correct for the standard errors. Okay, we correct for the cluster standard errors. By the way, this was a fixed effect that we did. The one I said is the best one among them. Okay, so how do we correct for the standard errors? Well, as always, somebody the other time was so happy with Newey West. And again, you can dump into that. So one way to do that is to get your library LM package and use this command to define the clusters for the individual identifier in the data set. So we do that. And this is a result. I want to show you just the standard errors, just the standard errors. So the only thing that is changing here is this. Sorry, is the standard errors. That one. So these standard errors have changed from the previous standard errors. How do I know that? Well, check the previous standard errors. Check for union. Check for union. It is 0.0193. That is union. Okay. Check the union here. It's 0.0227. So the standard errors is the only thing that changed. I'm not going to bore ourselves much. Okay, so that one was just correcting for heteroscedasticity. But this one here, it corrects for both heteroscedasticity and autocorrelation. So we use this command to be able to now come out with that solution. The command, the vconv, gave us a HAC before. A vconv is a function. It's a function for estimating a robust standard error of parameters for a panel model according to a man known as Driscoll and Craig. Okay. And this is consistent. I love this one because it's consistent not only to serial correlation, but it's also consistent with cross-sectional and serial correlation. It is consistent. This is a result for the Newey West, which is the one we just spoke about. And again, you can see that all of the variables are significant. Wherever Newey West is going, it brings some positivism because it's correcting for three things. Correcting for cross-sectional independence, it's correcting for autocorrelation, it's correcting for heteroscedasticity. All right. So how do you compare the fixed effect and then the phase difference? Well, it's very simple. When the time period is 2, then the fixed effect is the same as the phase difference. When it's 2. Okay. But when it's more than 2, then they are not equal. They are not equal. And I have a video here that you can watch that will help you to be able to get a better understanding of the fixed effect. All right. So that is a theoretical underpinning of the fixed effect and then a bit of the practical aspect of it. Any question?